Hi, this is the particle model reverse the classroom. This is kind of like the plan through the unit itself, right? So what we do is you talk about the particle model itself, talk about density. There's the density required practical that I've got a full video on. Internal energy, conservation of mass, heating and cooling curves, specific heat capacity, specific latent heat. Gas pressure then is triple, as are the gas laws. And then what we've got is we've got an assessment at the end. Now, firstly, there's quite a number of units in this. So units of density are kilograms per meter cubed. Now, we could have kilograms per centimeter cubed, okay, depending on what they give you in the question. You could have grams per meter cubed. You could have grams per centimeter cubed. So it's a bit weird because at density there's almost like 4 different units depending on what they give you. Mass, kilograms. Volume, meters cubed. It could be centimeter cubed. Energy needed is joules. So as soon as it says anything to do with energy at all, it's always joules. Specific latent heat is joules per kilogram. Change in thermal energy. So even though it's change, it sounds a bit more complicated. If it's got energy in there, it's joules. Specific heat capacity, they love this one, it's joules per kilogram degrees C. Temperature change, again, because it says temperature, the change bit doesn't really make any difference, degrees C. And pressure is then measured in pascals. Now, particles. There's all sorts of different sort of tables and things like that you can come with all about particles. Okay, so this is the one that I tend to use. We've got solids, liquids, and gases. What you can do is you can see that the particles in a solid are all in nice, even rows. Okay, all nicely compacted together. Liquid, they are still close together, but there are then gaps appearing in between each one. And then with a gas, the particles are then all over the place. I've then split it up into kind of 4 different sort of titles. Strength of force of attraction between particles is very string. I think I put an O in there instead of string, so very strong. So the forces of attraction between each of those particles is very strong. The force of attraction between those 2 particles is strong, but less than a solid. The force of attraction between those 2 there is incredibly weak. Arrangement, regular and orderly. Okay, you can see that, all nice lines. Random, very random, very, very far apart, is in a gas. Packing, they're very closely packed together. They are closely packed, but further apart than solids. So what you do here is you have small gaps appearing. And then particles, or the packing in a gas, is then moving around freely in random straight lines. Motion. What we've got for motion is they vibrate in a fixed position. So pretty much what's happening, one of those particles there is just like shaking on the spot. In a liquid, they slide or roll over each other randomly. And the motion in a gas is they're far apart, no regular movement, and they are moving very fast. Now, change of state. Now again, there's tons and tons and tons of different diagrams for this, okay, with a change of state diagram. Okay, I quite like this one because it kind of shows it all in one go. I've just got to make one little change to it. So we've got solids. What happens is when it turns into a liquid, it melts. Think about it as water. When it goes from a liquid to a gas, it evaporates. Gas back to a liquid, condensation. Liquid to a solid, freezing. Okay, that's kind of like your water part. Sometimes, not very often, a solid can go straight into a gas. And what that is then called is sublimation. Now on this diagram, what we've got is we've got a gas turning back into a solid. They've put it down as desublimation. Now what I like to do is I like to call it deposition. Okay, it's just another word, right? And I always think about it. If you've got a gas and it appears on the desk as a solid, it's kind of deposited. so deposition. And the final thing is increase in internal energy. So this way here, solids have got low internal energy, gases have got high internal energy. Down this right hand side here, I'm not going to go through all these different words here because it kind of explains it on the diagram, except for the fact that conservation of mass is when substance changes state, the mass is conserved. So if you've got a kilogram of solid, it'll turn into a kilogram of liquid. And then that is a physical change where the whole process can then be reversed. Now, in this section, there is then the density required practical. So density, kilograms per meter cubed, mass would be kilograms, and volume would be meters cubed. Now, I'm not going to go through loads of detail about the density required practical. What you need to do is you need to go to the density required practical video where it shows it in a lot more detail. Now, the only thing I'm going to highlight in this required practical is the fact that there's 3 methods. Method number 1 is talking about a regular shaped object, where you've got to get the density of a regular shaped object. So like this shape here, okay, where you got a standard width, height, length. Method number 2 is where you've got to work out the density of a liquid. So for example, water. And number 3 is the density of an irregular shaped object. So I could ask you to work out the density of that if it was a 3-dimensional shape. Okay, but again, I'll just repeat, right, go to the video that talks about specifically the required practical for density. Internal energy. Now, the definition of internal energy is the energy stored inside a system by particles. So whatever you've got an object and it's got energy within it. Okay, that is the internal energy. And what that is, that's a combination of the kinetic, which is the movement energy, and the potential energy, which is the store of energy. So it's the total amount of movement and store of energy, which is the total amount of kinetic and potential energy. And I've then written it down as an equation at the bottom here, where internal energy is the amount of kinetic energy added to the amount of potential energy. Now, if we heat it, what can happen is it can change the energy stored within the system. So what heating causes, it can cause a change of state. Right? And as particles separate, the potential energy stores increases. Heating increases the temperature of a system and particles move faster. Right? So as you heat it, the potential energy gets bigger and the kinetic energy also gets bigger. Now, a heating and cooling graph, right? Now, these are great, right? They're very similar to the diagram we talked about before. So what you do is you start with your solid at the bottom here. Okay, when it gets to a certain temperature, which I've labeled as A, it then changes from A to B, which is then going from a solid to a liquid. All right, as it goes from a solid to a liquid, it's melting. Then it goes from a liquid, and that then could be vaporization, or it could even be evaporation. And then it then turns into a gas. Going in the opposite direction, a gas to a liquid is condensation. Liquid to a solid is then freezing. Okay, now as you're heating up, just like I talked about before, as you heat it, you get more kinetic energy in the system itself. Right, now what I've got here is got some really good words, right? Firstly, we've got specific latent heat. Specific latent heat is the amount of energy needed to change 1 kilogram of a substance's state. So that could be solid to liquid or liquid to gas. Right, but more specifically, what they're going to do is they're going to ask about specific latent heat of fusion or the specific latent heat of vaporization. So on this right hand side here, I've just drawn that graph that we had before, where we've got temperature at the side, we've got energy across the bottom, and the graph kind of goes up, flat, up, flat. So the specific latency of fusion is the energy needed to change 1 kilogram of solid into 1 kilogram of liquid at the same temperature. That is this flat bit here. So I'm just going to put fusion. So it's the amount of energy required to change 1 kilogram of a solid into 1 kilogram of a liquid, but the key to it then is the temperature stays the same. So even though you're continuously putting energy in, right, the temperature doesn't go up at all. Okay, so that is then the specific latent heat of fusion. The specific latent heat of vaporization is incredibly similar. It's the energy needed to change 1 kilogram of liquid into 1 kilogram of gas at the same temperature. So that is this flat bit here, right? And if you notice, it stays the same. So that there is the specific latent heat of vaporization. Okay, if you think about vapes at the moment, in a vape, what you got is you've got a liquid, which is here. Then what you do is you add energy to it, and it turns into a gas. Okay, that is the vaporization part. So specific latent heat of vaporization, okay, is the energy required to change 1 kilogram of liquid into 1 kilogram of gas, staying at the same temperature. Okay. The equation at the bottom here, delta E, which is change in energy, equals mass times the specific latent heat. Now there's another one, and this confuses people, right, because they sound very, very similar. So what we've now got is we've got the specific heat capacity. Now this is equally likely as the specific latent heat to be asked about, except for the fact that this also has a required practical. So specific heat capacity excuse me, is the energy needed to raise 1 kilogram of substance by 1 degree C. Okay, so if I've then got a block of metal, what that means is it's the amount of energy that I need to put into that if it weighs 1 kilogram, and I want to put the amount of energy in it to raise it by 1 degree C. Now, specific heat capacity depends on how much there is, what the substance is, and how much energy is put into it. Okay, so the equation for this is change in energy, which is delta E, mass times specific heat capacity times the temperature change. Now, like I said before, there is a specific heat capacity required practical. What you need to do is you need to go to the other video. Okay, so go to the other video, and what it'll do, it'll go through it in a lot of detail. Now, these are then the 5 questions. You write these questions into your exercise book, and then what you do is you answer them in full sentences. So question number 1, what is the specific heat capacity of a substance? I want the definition. What is internal energy a combination of, right? So I'm just going to put internal energy equals something plus something. What are the units of specific latent heat? Name 3 types of objects you need to calculate in density of. 1, 2, 3. And number 5, write the density equation with units.